in class, I gave you 3 circuits on the board, basically all solving the same Dell DC power supply, half, full, and bridge. This is the solution to the half-wave problem. The full and the bridge are also posted. This is not for marks, but you will be probably seeing circuits similar to this again. So we know that 19.5 volts DC was the average DC output. So what we need to do now is figure out what is the voltage peak output. If you'll recall, this is what we're looking for, right? Voltage peak output. So maybe over here as an aside, I'll wipe it out in a minute. Very quickly, VDC average in a half wave was the output voltage, right, divided by pi. So it's pretty quick manipulation. Divide both sides by pi, and V peak is equal to pi times VDC average, right? So I'll erase that. There we are. Sorry, in the previous ones I've solved that all the way through, but that's a pretty straightforward one there. So what we're going to have to do is take VDC average, and we're going to multiply it by pi. And that should tell us what the peak voltage is, and that's 19.5 volts times 3.14, which means that our output voltage was 61.23, I believe. 61.23 volts, and that's V peak out, right? So there's our 3 output voltages. So that means this is the peak output voltage of our power supply. You remember that the V peak out was equal to V peak secondary voltage, right, minus 0.7. That's an awful looking 7, isn't it? I can do a better job of that, I think. There. Seven. So again, we're looking for V peak secondary. We have V peak out, so it should be some straightforward manipulation. V peak secondary is going to be now equal to V peak out plus 0.7. That's now going to be 61.23 plus 0.7, which is 61.93 volts peak, and of course that's V peak secondary. So we now have the output voltage, we now have the peak secondary voltage. Again, V peak primary, remember, was 120 RMS, which is 169. Oh, see there? That's some good work, eh? As I told you, if you're paying attention in earlier classes, 169.7 is primary. The secondary voltage that we're looking for is 61.93. When we divide 169.7 by 61.93, we end up with a turns ratio of 2.74 to 1. So if we had that turns ratio and one diode, we could calculate this. Of course, we'd want to consider how much current it has to pass, so we would need to know the connected load, and then we could find the current through the circuit. We'll do a couple of those on the board in class. The other option, of course, here is that we would want to know, when it's during the negative alternation, what is my peak inverse voltage, or how much does it have to hold back? Well, conveniently in this situation, the peak inverse voltage is equal to the peak secondary voltage. It has to hold back the entire secondary, which, as you recall from over here, was 61.93 volts. So there you have it. And as I said, if I knew what the connected load was, so in this case, if I knew the laptop with a dead battery, what was a certain current draw drew so many watts or so many amps, I could then do the math and figure out how much current is going to be flowing through here, peak, and pick a diode that can handle this much forward current, this much voltage, and this much reverse bias current. And again, you could just now make this power supply if you needed a particular voltage.